Good morning. In today's lecture, we'll start talking about a new class of organic compounds known as alkenes. Alkenes are hydrocarbons, just like alkanes, but unlike alkanes, they have a CC double bond, which significantly influences their chemical properties. Alkenes are also sometimes known as, sometimes referred to as olefins, although that is an old name which we'll try to not use quite as much. Alkenes are hugely important in industry. They occur in nature in multiple locations, and I'll give you just a couple of examples of alkenes that we encounter in everyday life. This is the simplistic alkene known as ethene, which on one hand is an important industrial feedstock. It's a hugely important industrial feedstock. On the other hand, it's also a ripening hormone in plants. So if you leave your fruits or vegetables in a plastic bag, you will see that they ripen quickly because that allows ethene, which plants emit, to stay put and to further influence their ripening. Another example of a very aromatic alkene is this compound known as alpha-pinene, which is a component of turpentine. An alkene which finds its applications in nutrition is this long-chain alkene, which is also a carboxylic acid, and this is the oleic acid. Oleic acid is a component of olive oil, and it's found to be very beneficial in terms of health effects. This is probably related to our discussion of pesticides based on halogenated systems. A new generation of pesticides includes this compound, which has a huge carbon chain, about 30 atoms long. And this compound is called muscular, and it's a pheromone. And pheromone is a sexual attractant of the common housefly. Many other insects have these pheromones, and they really represent a new class of pesticides, because they sort of allow you to launch a psychological warfare onto insects, because they can be used in very small concentrations and they're virtually non-toxic. They're completely non-toxic actually, and they can be used to attract insects to one spot where they would expect to find their mates, where they can be poisoned in a simultaneous fashion. So that sort of represents a new, very, very selective class of pesticides that's been developed. So point of this whole thing is that their alkenes are really everywhere, and they occur both in industry and nature very predominantly, so they're an important class of compounds. If we look at the orbital picture of alkenes, and this is really how our discussion will begin, then you might remember that alkenes have sp2 hybridized carbon atoms, which have one p orbital left untouched by this sp2 hybridization, which forms the pi bond, whereas the sp2 orbitals form the sigma bond. So the alkene double bond is not symmetrical. There are two components to it which are quite different. So p orbital is a side-on overlap, and it's a relatively weak overlap, while the sigma orbital is a head-on overlap, which is relatively strong. Okay. Now, CC bond is both shorter and stronger than the CC single bond. If you look at the comparison between the ethene and ethane, we can compare a couple of parameters. These are the bond lengths between CH bonds are roughly identical. But the CC bond is significantly shorter here. It's 1.33 angstroms. Here it's 1.54 angstroms. The angles are also quite different. This angle is 109 degrees. This angle is about 116 degrees here. and 121 degrees here. So there are quite some differences, but the point is that the CC bond is shorter and stronger than CC single bond. And CC single bond. Okay. Well, let's look at some numbers, see how much shorter is it. We've seen how much shorter it is, but let's look at the strength. The CC bond is found to have a bond dissociation energy of 146 kilocalories per mole. You'll see that this is quite a large number compared to the normal CC single bond, which has the same value of bond dissociation energy of 83 kilocalories. From this, we can estimate that the C-pi bond has a bond dissociation energy of 63 kilocalories per mole, which means that it's weaker than the sigma bond. Okay, and this is an important finding because it means that most alkene reactivity is focused here, focused on the pi bond. Another important factor is the rigidity of the double bond. So if we look at the alkenes, we already know that there are cis-trans isomers that we can isolate that are stable compounds. So this will be a cis isomer. But if we wanted to get to a trans isomer of the same compound, which would look like this, we wouldn't be able to simply do that without breaking a CC pi bond. So if we theoretically wanted to pursue this and get to the trans isomer, then our transition state would involve complete loss of overlap between the two pi orbitals, which would be energetically significantly unfavorable since the pi bond has to be broken. So pi bond would have to be broken for rotation to occur. This reaction actually does occur. If we expose alkenes to typically UV light, the pi bond does break, and you can see the rotation isomerization between the cis and trans isomers. But as I said, it's not a common reaction and doesn't occur spontaneously. So for all practical purposes, cis and trans isomers are stable compounds which do not interconvert unless exposed to pre-extreme conditions. In the next subtopic, we will see a little bit more about quantitative analysis associated with the presence of double bonds in alkenes and other molecules.